Hey everybody, I just wanted to make a few quick notes before your final exam tomorrow on some of the most common errors that I saw in exam 4. So let's go through a few of the examples. If I ask you to find 4 raised to the 3/2 power, we know we can rewrite this as 4 times 3 raised to the 3 times a half, and then I can take the root first, so I'm going to take the 1/2 root of 4, that's a square root, and raise it to the third. Remember, our rules of exponents say that 3 times a half as an exponent would be the same as taking 4 to the 1/2 and raising to the third. So now you can take the square root of 4, which is 2, and then cube it, and you'll get 8. Now, over here, this is the same kind of thing. This is minus 4 raised to the 3 times 1/2, and so what you have is minus 4 to the 1/2, all raised to the third. But really, that's the square root of negative 4 to the third, and we cannot take the square root of a negative number, so this does not exist. Now this is very different than if I wrote minus 4 to the 3/2. Notice there's no parentheses here. The exponent only applies to what immediately precedes it, which would be the 4. So therefore you can kind of rewrite this as minus 1 times 4 to the 3/2, and you would end up with minus 8 if you did this. Alright, so that's just a little warning. That wasn't on the exam, but something to make note of. Let's check this one out. With a negative exponent, what you first want to do is move the entire term to the basement and make the exponent positive. Now we can run through the same progression where we look at the 1/2 root of 9 first and then cube that. So notice the denominator here is your root and the numerator is the power when I come over here. So this is really 1 over 3 cubed, which is 1/27. That's where the 1/27th comes from. Similarly, for 8 to the minus 2/3, you first make the power positive by moving it to the basement. I'm then going to take 8 to the 8 to the 1/3, that's the root, and I'm going to square that. The third root of 8 is 2, and we have that squared, and that's where we get 1/4 as the answer. Next, the square root of y squared plus 16. As much as you want to write that this is y plus 4, this is not allowed, cannot happen, so you got to really resist that urge. This expression cannot be simplified, and it is simply the square root of y squared plus 16. Alright, so be aware of that. We cannot distribute the square root over addition. Next, if I'm going to expand the square root of x plus the square root of 5 squared, you're going to have the square root of x plus square root of 5 times square root of x plus square root of 5. So many of you did that correctly. We will distribute this to both terms. So you get root x plus root x root 5. Then we distribute this. So that's plus root 5 root x plus root 5 root 5. Most of you got to that point. This is just x. The next piece is square root of 5x. That's this piece. The next piece is square root of 5x. So I'm using the product rule there to get them all inside the square root. And the final piece ends up being 5. So a lot of people got to this step, but then they wanted to write this as the square root of 10x, which is not the case. What this ends up being is 2 times the square root of 5x. All right, so there's no rule that says we can take the square root outside of a sum. So the answer is x plus 2 root 5x plus 5. A few more here. A very common thing on this problem was to want to use some sort of exponent rule to combine these, and that exponent rule actually doesn't exist. You can think of this, say I had x to the 9th minus x to the 5th. This is not equal to x to the 4th. These terms here can just not be combined. They're not like terms. So the only way to simplify this expression is to distribute this into both pieces. And when you do that, you get x to the 1/4 times x to the 3/4 minus x to the 1/4 times x to the 5/4. Okay? And then what we can do in this term here, you add the exponents because that's the rule of exponents here. x to the a times x to the b is x to the a plus b, so we add, and here we add as well. And in the end you'll get x to the 4/4, which is 1, minus x to the 6/4, which is really 3/2. And these cannot be combined, they're not like terms, so we have to leave it in that form. And finally, these last two guys. In this one, we have the cubed root of 125, a to the 7th, b to the 6th. What we want to do is take each of the pieces, so 125, that's actually a perfect cube, that's fine. I'm going to split the a to the 7th and take out the largest factor of 3, which in this case is 6, times a. And for the b to the 6th, I'm going to leave that as b to the 6th. Now the product rule says I can split it up over each of these factors. So I have the cube root of 125, cube root of a to the 6th, cube root of a, and the cube root of b to the 6th. This first piece is 5. This is a squared. This is cube root of a, and this is b squared. So our final answer is 5a squared b squared cubed root of a. You'll have one just like that on the exam tomorrow. And finally, over here on this last problem, everyone wanted to distribute this square root over the addition, meaning they wanted to write this as such. Plus the square root of 8x squared y squared. And that is not the case. We cannot do that. It's actually illegal. What we can do, however, is take out the GCF from both of the terms on the inside of the square root. So I'm going to pull out a 4, x squared y squared. And what that leaves you with is y on the first term and a plus 2 on the second term. So now we have really two factors. We've got this and we've got this. And now we can use the product rule, which says that that's equal to the square root of 4 x squared y squared times the square root of y plus 2. And that first piece ends up being 2xy when you take the square root of each of those pieces, and this is y plus 2. So be very careful with square roots over addition, guys. Hopefully this helps. I'll see you all tomorrow.